Okay, so in chapter 8, section 6, we're talking about the Pythagorean theorem. And there was a commercial a couple of years ago about where they mentioned Pythagoras. They said it in a funny way. I should look that up. There was a man back in ancient where? Probably Greece, who was into triangles, really into triangles. His name was Pythagoras. And he found these interesting relationships of the sides and of the angles and so on of triangles. And so this little image of him here, Pythagoras, there he is. Just a little statue. They didn't have a camera, so there's a statue of Pythagoras. And he's most well known for this theorem that he developed. Does anybody know it already? Or we say it? Okay, you'll know it today. When it comes to right triangles in particular, there's an amazing relationship between the sides. So a right triangle is called a right triangle because it has a right angle. Good. And a right angle is how many degrees? 90 degrees. So it has one 90-degree angle. Let me pause this for a second. Okay, so I have the words covered now. So here we have a right triangle. So sketch out a little right triangle. We know it is because it has a symbol for a 90-degree angle in the corner. Okay, so before we look at the relationship he found, the relationship of the sides of a right triangle, we are going to identify what we would call these things. So this is, as you can see, the right angle. Oh, you guys, well, sorry. You guys can't see. I can see. You know, this remote is not working very well. There, sorry. Let me pause this so you can. Okay, so there are three sides to every triangle. And one of them is always the longest side. And the longest side is always located across from, guess what? The right angle. Good. So the right angle, the 90-degree angle in this image is here, and across from it is the longest side. Now, could we have an angle, the other two angles? Is it really frozen? Okay, so the other two angles must add up to how many degrees? Emily? 90 degrees. So could either of them be 90 degrees? Could we, Juliana, could we have two 90-degree angles in a triangle? No, because it would be 180 degrees taken up already, right? So they must be less than 90 degrees. They must be, what do you call angles that are less than 90 degrees? Acute, little angles, acute angles. So these other two sides are across from the acute angles. And this long side is across from the largest angle. So because it is the largest angle, the longest side is across from it. Okay? And that side has a special name. Does anyone know it? It's kind of a Greek word, the hypotenuse. Hypotenuse. Can you say that? Hypotenuse. It's always the longest side of a right triangle. When we give labels to the sides, that side is most often labeled C. So we'll put that there now. You can see the other two sides are A and B today. And that's usually the case with right triangles too. They're just the shorter sides. Now in this right triangle, one of them is shorter than the other, right? Could it be possible for us to have a isosceles right triangle? To A and B the same? It is possible. So sometimes they're the same in an isosceles, but in this case, it looks like A is shorter than B. Okay? So we just say that the shorter legs in a right triangle are just called legs. There's nothing Greek about that, I guess. They're just legs. So when somebody says to you the legs of the right triangle, you know they're not talking about what side? The hypotenuse, because that is not called the leg, that is the hypotenuse. It's the key term here. So what is so interesting about a right triangle's legs? So I have a little coordinate plane here so we can kind of see what Pythagoras discovered. We have X and Y, I discovered. So what he discovered is with any right triangle, so let's put together a right triangle. Let me go, there's 10 units in each direction. So let me go like up 3 and over 4. 1, 2, 3, 4. And so I'm going to connect those two endpoints. And there we have a little right triangle. Okay? So we have a symbol for a right triangle right there. And we said that the letter given to the hypotenuse most often is what letter? C. Say it louder. Good. C. The other sides we just could call A and B, the legs. So what he found was, if you take the length of a leg, let's take the length of A. How long is it? How long is that? How many units is A? 3. Okay? So if I take 3 and I make a box on the back of that leg, a square actually, that is 3 by 3, what is the area of that square? 3 rows of 3? What is it? 9. You guys are so silent. This has an area of 9 units. Okay? We could do the same on the side that has, the side that's labeled B right here. What is the length of side B? Leslie, say it. 4. So if we put a box here, we could make a square that is 4 by 4, kind of on the back of that leg. And what would the area be of this square? 4 times 4 is? 16. Okay. And what he noticed was, if you take the hypotenuse and make a square on the back of the hypotenuse, it's kind of, I'm just kind of eyeballing it, kind of estimating it. We know that that side C is longer than A and B. We said A is 3, right? B is 4, and this is the most common right triangle on the planet. Guess how long C is? Very good. Good guess. It's 5. So if C is 5, what is the area of the square that we put on the back of C? 5 times 5 is 25. So now when we look at these numbers, 9, 16, and 25, can you find the relationship that Pythagoras found? 9, 16, and 25. Thumbs up when you find it. 1, 2. How are these numbers related? 9, 16, and 25. 1, 2, 3, 4. Can you find it? Dylan, how are they related?
Well, 9 is a multiple of 3.
Okay.
3 times 3, 16 is 4 times 4, and 25
It's 5 times 5. Okay, so we already kind of established that relationship because we said that this is the most common right triangle. What else do you see with these numbers? And this is what Pythagoras found too. Lauren?
They all have squares.
Well, they're all perfect squares. Good. Emily?
You add 9 and 16 together, you get 28.
Very good. When you add these two, 9 plus 16 equals 25. And this is true of all right triangles. If you take the small legs, A and B, and you add their squares, you will always get the square of the hypotenuse. And that is the Pythagorean theorem. And it's because of what you see in this image here. Square the legs and you will get the square of the hypotenuse. So let's jot that down in a rule box. This is only for right triangles, but right triangles are extremely useful in the real world. We can change a lot of real world questions into right triangles. And so when we do, we call the hypotenuse C, the legs A and B, and there you have it. The sum of the squares of the legs equals the square of the hypotenuse. So realize that you have to square these legs, don't you? It doesn't work if you just add the lengths of the sides. Like, how long is side A? 7th grade, how long is side A?
3.
3. What's 3 plus side B? What's 3 plus 4? 7. Does 7 equal side C 5? No. But when you square it, you have 9 plus 16, you get 25. And it works for all right triangles. Okay? So it's a simple little formula, a squared plus b squared equals c squared. And so we'll use it now to find lengths. We can use it to find any given, any missing side of a triangle. As long as we know 2 sides, we can find the third. Okay? So our first question is find the length of a hypotenuse if the triangle has legs of 28 centimeters and 45 centimeters. Jot that down. And what would the length of the hypotenuse be? Yeah? Okay, so we always start in our geometry with the formulas, and we have this formula, a squared plus b squared equals c squared. So where do we input the given information? Charlie, what would you say? Okay, so how would I write the new equation? Okay, so he's saying the unknown side is C. Thumbs up if you agree? Yes, that's the side we need this time. We could be given the hypotenuse, but we weren't. We're finding it. Okay, so this is kind of tricky numbers. Have you done it? What is 28 squared, right?
I got 784.
Does anyone agree? 784? Good. I have agreement, so I'll go with it. And 45 squared, does anyone have that? Nicholas? 2025, does anyone agree with that? Okay, good. 2025 equals c squared. So we simply add these. 4 plus 5 is 9. 8 plus 2 is 10. Carry a 1, right? 7 plus 1 is 8. And 2,809 is c squared. So how do we find c? What do you do to a squared term to isolate it? Lauren? What's the inverse of squaring? Take the square root. So take the square root of both sides. Okay? And so it would be nice to have a calculator. But if you didn't, we already know that 45 squared equals this number. So the square root of 2,809 must be bigger than 45, right? What would 50 squared be? That's one of those easy numbers. 50 squared is 5 squared. 5 squared with 2 zeros. 50 squared is? 50 squared is 25 with 2 zeros, so 2,500. Okay, so is this thing greater or less than 2,500?
Greater.
Greater. So let's go to 60 squared. 60 squared would be what?
3,600.
36 with 2 zeros. Good. So this is less than 60 squared. It's somewhere between 50 and 60. What is it closer to? It's closer to 50, right? And then the thing ends in a 9. Do you see that? So I might try 50 something that would end in a 9. What if I tried 51, would 1 times 1 end in a 9? 52, 2 times 2 would end in a
I got it.
4. 53,
53.
3 times 3 ends in a, it does end in a 9. What is 53 squared? Try it. Have you done it?
Yes.
And it is?
2,809.
It is the number that we are looking for. So the square root of 2,809 is 53. And that seems reasonable looking at the numbers that we have. 28 and 45 are both smaller than this hypotenuse 53. Okay? Okay, so now we are going to find the missing sides of these right triangles. So always start with the formula, and you'll have to pause and come back and view the answers. So if you need to pause the video and take a look at how this was found, you can do that, but here we have the correct answers by Lauren and Chris. And so there you go. Have a good